Hey folks, welcome back. In this video we're going to go over two worked examples to show you how to do problems involving the effect of irradiance on kinetic energy and photoemission. Now if you haven't already done so, check out my previous video covering the theory on this topic, and that way you can apply what you learned in that video to this one. So let's get going. Question 1 says that ultraviolet radiation causes the emission of photoelectrons from an aluminium plate. The irradiance of the radiation is increased. What effect does this have on A. the maximum kinetic energy of an emitted photoelectron? Well, remember irradiance has no effect on the maximum kinetic energy of an emitted photoelectron. And for part B, what effect does this have on the maximum speed of an emitted photoelectron? Well, remember that kinetic energy and speed are directly proportional through the equation Ek equals 1/2 mv squared. So that means whatever happens to the kinetic energy happens to the speed as well. So we can say that increasing irradiance has no effect on the maximum speed of an emitted photoelectron. And lastly, part C says what effect does this have on the number of photoelectrons emitted per second, otherwise known as the photoelectric current? Well, remember, if the irradiance of the radiation is increased, this means that more photons are instant on the metal plate each second, which means that the number of photoelectrons emitted per second will increase, because remember the photoelectric effect is a 1v1 process where one photon absorbed by the plate is equal to one photon emitted by the plate. So we could say that increasing the irradiance increases the number of photoelectrons emitted per second. Part D says to sketch a graph to show the relationship between the maximum kinetic energy of photoelectrons and irradiance. Well, we've just said that irradiance will have no effect on it, so your graph should look something like this. So if that's maximum kinetic energy of photoelectrons on the y-axis and then irradiance on the x-axis, you should have a straight line going along the way showing that constant relationship. And lastly, part E says to sketch a graph to show the relationship between photoelectric current and irradiance. Well, we've just said that photoelectric current will increase as irradiance is increased, so we need to show this directly proportional relationship. So your graph should look something like this. So if you plot photoelectric current on the y-axis against irradiance on the x-axis, for frequencies greater than the threshold frequency f0, you should show a line going straight through the origin. Lastly, question 2 says the following apparatus is set up in a physics lab to investigate the photoelectric effect. So we have this circuit here where we've got a glass tube and a vacuum inside. We've then got a sodium plate on the left hand side, and we've got some instant light passing through this window to hit the sodium plate. We've also got an ammeter so that we could take a reading of current. It tells us that the work function of sodium is 3.78 times 10 to the minus 19 joules, and that light of frequency 6.74 times 10 to the 14 Hz is instant on the sodium plate and photoelectrons are emitted. Part A says to calculate the maximum kinetic energy of a photoelectron just as it is emitted from the sodium plate. Well, writing down what we know from the question, we're trying to find Ek. We know that Planck's constant H is 6.63 times 10 to the minus 34 joule seconds from the datasheet. We know the frequency f of the instant photons is 6.74 times 10 to the 14 Hz from the question, and we know that HF0, the work function of the metal, is 3.78 times 10 to the minus 19 joules. So writing down our equation for maximum kinetic energy, we have Ek equals HF minus HF0, substituting in the numbers, gives 6.63 times 10 to the minus 34 times 6.74 times 10 to the 14 minus 3.78 times 10 to the minus 19, and if you put all of that into your calculator, you should get an answer of 6.9 times 10 to the minus 20 joules. Part B says to calculate the maximum speed of a photoelectron just as it is emitted from the sodium plate. Well, notice that we've just calculated the maximum kinetic energy, so we can use that now to calculate the maximum speed. So we're trying to find the speed v. We know that Ek is 6.9 times 10 to the minus 20 joules from part A there, and we know the mass of an electron is 9.11 times 10 to the minus 31 kilograms from your datasheet. So writing down our equation relating kinetic energy, mass and speed, we have Ek equals 1/2 mv squared. Substituting in the numbers gives 6.9 times 10 to the minus 20 equals 1/2 times 9.11 times 10 to the minus 31 times v squared. Now what we could do is multiply both sides by 2 to get rid of this half, and then divide both sides by 9.11 times 10 to the minus 31, and that will give us an answer for v squared, which should give you 1.5 times 10 to the 11. And if you then take the square root of both sides, you'll get v on its own, so doing that in a calculator should give you an answer of v equals 3.9 times 10 to the 5 meters per second. Lastly, part C says the irradiance of this instant light is now decreased. Explain the effect, if any, that this has on the maximum speed of a photoelectron just as it is emitted from the sodium plate. Well, remember we saw in question 1 that irradiance will have no effect on the maximum speed of a photoelectron as well as the maximum kinetic energy. So that means we can say here no effect. Irradiance does not affect the maximum kinetic energy of photoelectrons and therefore does not affect their maximum speed. That's all for this video folks, thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.